Now if that's empty, well, that means, therefore, M does not accept W. Okay, whatever your W is. Is that obvious? Because imagine that M did accept W. Well, therefore, that W would be a string that it accepts, and that would not be the empty string because there's at least one string in it in the language. Okay. All right. So if R accepts when you input this, that means that your language is empty. Right? Okay. But so that's fine. So, but what happens if R rejects? How do you interpret that? What does that mean? Well, all we know is that that the language here is not the empty set, okay? Because that's what R is testing for, right? It takes a description of a Turing machine, M angular brackets is input, and asks whether the language of that machine M is empty. Okay, so if that machine R rejects, what does that mean? It means that the language of that machine, the L of M, is not empty. Okay, so there's at least one string that this language here is not empty. Okay, that it's not empty. Okay, so that means this M is accepting some string. But the point is that we don't know whether M is accepting the particular string W. It could be any other string. Right? Or we know all that R is telling us is that this is not empty. That's it. But it's not telling us. We don't know. It could be some other string, not non-W, that's causing this L of M to be non-empty. So that's the problem. Okay. So we've got a problem there. So we can't use R because it's not giving us information about our particular W. See, if we want S to decide on the language ATM, and that's the whole point of the proof. We're trying to have S decide ATM, because that would then be our contradiction, right? And if we can show that ATM is decidable, then we have a contradiction, because we know, prior knowledge, that ATM is undecidable. Alright, so we're trying to get the larger Turing machine S to decide ATM. Now how do you decide ATM? Well, that means that the ordered pair M, W, that's a member of that language ATM if M accepts W. Right? So we're talking about a particular W, but by using R here, all we know is this, but we don't know which this non-empty language, which string made it non-empty. Is it W or something else? That's the problem. It could be something else. So we need a different idea. Right? That's not going to work. Now the idea now is we're going to take M, this machine, and we're going to modify it. We're going to create a variation of M, and the modification is such that it will reject all strings except W. So there's a kind of pre-filter, if you like. So any string coming into M modified, M dashed, if you like, will be rejected by M dashed. Any string coming in will be rejected by M dashed if it is not equal to W. Right? That's the modification we will use. I hope now you can see where I'm going with this, right? Alright, so now we can go back and use R again, but this time with M modified, we have more information. So if let's see, so we'll use NRR to see whether machine M, or modified machine, or M dash, let's say, the modified machine, will recognizes the empty language. Let's see. Now this modified machine, remember, M dash, the only string that it can accept is W, right? Can accept. Because all the others, all the non-Ws, they automatically get rejected. Okay? So the only way R will reject, in other words, the language is non-empty, is if and only if. Okay. Let's see. What does it refer to? I mean, just common sense. So we've got this modified machine, and it rejects all strings that aren't W. Okay, so the only string that won't be rejected is W. Okay, now put that ordered pair M dashed, comma, W into your ATM. What will ATM do? So M dashed, comma, W. So the W will go through the M dashed filter, right? Because it is equal to W, so it goes through, and then M dashed behaves as if it's W, so as if it's M before it was modified. So if M accepts W, have your S reject. Why is that? Well, because you're no, hold on. It's an ATM. Have it accept, because we want it to behave like an A. The language ATM, because by definition the ordered pair in ATM, all those members, that means the machine M accepts the string W. Okay. I'm trying to keep all this in my head, not easy. Thinking real time here. Okay, so so what happens when the ordered pair M dash, or M modified, comma, W goes into S, and S is supposed to be behaving, is supposed to be deciding the strings, the elements of ATM. Okay, so M dashed, comma, W. Now because it's M dashed, the only string that gets through the filter is W. And then M dash just behaves as M. So now effectively we've got M, comma, W. We know it's that particular W, the one we're testing. So if M accepts W, have S accept. If M rejects W, have S reject. Okay? And therefore S is a decider. Right? because it's either accepting or rejecting. And there's your contradiction. Because if S is a decider, that makes ATM a decidable language, and that's just not true, because we know that ATM is undecidable. Okay, follow me. Getting a bit tougher, but I hope you followed that logic. If I haven't made a stupid mistake. So it's like if no method accepts W, right? If R accepts, doesn't accept anything. Does not accept it. Well, let's word it somewhat differently. Well, study that, study what I said, and reflect on it, and then next board we will go into the more detailed proof. All this is just proof idea, and it's getting tougher. Ciao.